Hello everyone, welcome to my presentation video in Thessaloniki GECKO days. My topic is implementation of EGA in the design and analysis workflow of machine elements and systems. As we know, the contact mechanics plays a very important role in the machine elements and systems. So in this presentation, I will discuss our investigation of a Hertz contact based on EGA. And first, let's have a look at two classical Hertz contact models, the contact between two spheres and the contact between two cylinders. And in the contact between two spheres, we can see the circular contact area resulting in a semi-elliptic pressure distribution, and in the contact between two cylinders, the contact area, it becomes a rectangular stripe extending along the cylinder axis. So now let's see how to get the theory solution of the contact pressure. Here we can see the contact half-width. It depends on the material properties and the applied load, and also the radius of the spheres or cylinders. And here is the formulation of the pressure. Here we can see the pressure distribution follows an elliptical profile. And in our study, we use the following material parameters and also the penalty method here. So here, given the penalty factor is given here. And during the simulation, the contact simulation, the two body omega-1 and omega-2, and also the target contact boundary C1 and C2, and at phi 1 and phi 2, they approach to each other until the common contact boundary together. And in the penalty method, the contact is detected based on the normal gap denoted as Gn. It represents the distance between two potential contact surface measured along the normal direction. So when Gn larger than 0, it's defined as separation. And when the Gn smaller than 0, it's defined as penetration. You can take it as contact status. And here, to resist this penetration, a contact force is introduced, which is proportional to the gap Gn. And when the contact occurs, the two bodies should not penetrate each other. However, their original stiffness matrix only describe their own material deformations, not the resistance to contact between the two models. So here, the extra stiffness matrix proportional to the penalty factor act like a spring between the two bodies. So in this way, the contact constraint is approximately enforced, while still allowing a small controllable penetration for numerical stability. And here, to evaluate the accuracy of our IG results, and we compare them with the analytical Hertz solution, we use two main error measures, the maximum pressure relative error, and this shows the difference between the peak contact pressure from the simulation and from the theory value, and also the L2 normal error. This one measures the overall deviation of the pressure distribution along the contact area, it providing a global accuracy indicator. And now we show our Hertz contact 2D model. Here, this is the initial EGA control points net, it defines the geometry of a 2D cylinder. And here, according to the Saint-Venant principle, the local stress and the deformation near the contact region are not affected by the boundary condition far away from it. Therefore, we can safely use the simplified 2D cylinder contact model to study the local contact behavior with good accuracy. So in the following investigation, we just use the model in the shadow area and also here. Here I want to introduce the EGA H refinement, these characters. H refinement involves refining the mesh by inserting new nodes, for example here. And for degree 2 spline, node insertion adds new nodes, increasing the number of elements here from 2 elements to 1, 2, 3, 4, 4 elements, but it doesn't change the curve shape. And also the repeated nodes, or it reduces the continuity of basis function at the location here, but it still keeps the same shape. This allows the local refinement while preserving the exact geometry, which is particularly useful for accurately capturing the contact stress. Here you can see a 2D cylinder, deformable, and a half space, which is rigid. The parametric domain is refined locally in both U direction and V direction, focusing on the contact region. And in the physical space, you can see here it's very refined meshes. And here you can see the average and minimum element size, parametric range, physical coordinates, and also the element numbers in these refined areas. And in this one, we extract the contact boundary to identify the contact pairs. Each contact pair here, they represent a potential interaction point between the two boundaries. And also based on the penalty method, a contact force is introduced for each pair, which is proportional to the gap. Here we can see the EGA the EGA results contact pressure matches the analytical Hertz solution very well. And you can see the maximum contact pressure is within 0.3%, and also the L2 normal error, it's very small. Here it shows the displacement in Y direction and the stress. Here, if we refine the mesh uniformly instead of inserting nodes near the contact area, we would need many more elements to achieve similar resolutions. So, but even then, the accuracy near the contact region might be still be lower compared with a locally refined mesh. So this shows that the targeted H refinement in the contact region is much more efficient and effective for capturing the contact stress. Here we just consider about the contact between a 3D deformable cylinder and a rigid half space. At the cross section halfway along the cylinder length, the contact pressure from the simplified model agrees well with the theoretical Hertz solution, with the error within 1%. However, Along the length of the cylinder, the simplified model shows the contact pressure increasing from 400 to 750. It indicating the variation that the simplified model might cannot fully capture the contact pressure change. So we need to explore a full 3 model to study the contact pressure distribution more accurately. So next one, we come to the full model, and this is the contact. We extract the contact surface, and here we see the contact pressure along the cylinder length shows a symmetric distribution, and because near the ends of the cylinder the surfaces are free, so it allows some stress relaxation. So here the value is more small than in the middle. This highlights the importance of using the full 3D model to capture the realistic pressure variation along the cylinder length. Okay, let's come to the next example. We replace the rigid half space into deformable half space, and so that means we make both bodies deformable. And here we see the final contact pairs are extracted and visualized. It shows the interaction between the two surfaces. And this setup allows us to study the mutual deformation and the more realistic contact pressure distribution compared to the rigid half-space case. We visualize the displacement of the bodies in y direction, which corresponds to the direction of the applied load, and at the same time the normal stress sigma yy is shown, highlighting how the material responds to the contact force. And we also use a different simplification modeling, and we only choose the right half side of the domain, and the mesh is locally refined near the contact region to improve the accuracy, and the contact boundary is extracted, and the final contact pairs is showing here. These approaches also reduce computational cost while still capturing the essential contact behavior. Here we can see the contact pressure from the simplified right half model. It matched the analytical Hertz solution very well, and here shows the displacement in y direction along the applied load. It's also captured accurately. And now we come to the 3D example. First, we extract the contact surface, and we can see the contact pressure shows excellent agree with the analytical solution. The maximum relative error is within 0.3%, and the L2 normal error it's around 2. And also the contact pressure distribution along the cylinder length is symmetric, reflecting the uniform boundary conditions and the full 3D modeling. Here we study another model, 2D cylinder and cylinder to deformable cylinder contact. This example it's also meshed locally in the contact region, and also here you see the final contact pairs are extracted and visualized. It shows the points of interaction between the two cylinder contact boundaries. Here, you can see the IGA predict contact pressure matches the analytical Hertz solution very closely. The maximum relative error is within 0.2%, and the L2 normal error, it's the largest one, it's 2. It really indicates a very excellent overall accuracy. Here we come to the 3D cylinder deformable models, and we can see the contact pressure agrees with the theoretical very well, and also the symmetric contact pressure distribution along the length. Here, we introduced a new model consisting of two truncated conic solids with parallel axes. The larger ends of the cones are constrained in displacement, while a load is applied along the axis. So the system will achieve a balance, a static equilibrium. It allowing us to study the contact behavior between the contact surfaces. Here we just show the simplified truncated conic model. And why do we choose the truncated model? Because we want to, our final goal is to study the contact between helical tooths. So the helical planetary gears involves a complex 3D contact between the curved tooth surface. And it makes direct analysis computational expensive. Oh, sorry. I couldn't go to the former page. And also because the helical teeth along the y direction, the curvature it changes. It's so the truncated conic contact model, it just mimic the helical gear contact. Here you can see the physical info and the actual distance, and also the materials, the load. Here, along the length of the contact surface, the curvature of surface changes. And so according to the Hertz theory, the contact half-width is inversely proportional to the square root of the sum of surface curvatures. And at the same time, the maximum contact pressure is inversely proportional to the contact half-width. Therefore, along the length of the contact pressure, it decreases where the surfaces become flatter following the curvature variation. And here we extract the contact surface from the two truncated conies, and the potential contact pairs are identified between these surfaces. You can see that. Here, the normalized contact pressure distribution along the contact length of the cones, it follows the theoretical trends. As predicted by Hertz theory, the pressure decreases along the length where the surface flatten. And we also performed the finite element simulation in Abacus to compute the contact behaviors. And here shows the contact pressure distribution. And also, we also visualized the sigma 22 in IGA solution. And here we visualize the stress distribution from different perspectives. Multiple views help us to fully understand the deformation and stress behavior in the contact region. And here we can see the IGA solution and also the abacus solution as a comparison. For MySys IGA solution, and from multiple perspectives, and also the IGA solution for MySys and from abacus solutions. Here we compare the for MySys stresses and sigma YY for the two truncated cones, the IGA results and the abacus finite element results are in good agreement. So this confirms IGA can capture the contact stress. It is comparable to the conventional finite element method. Thank you for listening to my presentation. Have a nice day. Bye bye.